All right, guys. So we move to the next question, which is question number 11. Now, question number 11, we have highest thermal expansion is seen in option A, solid, option B, liquid, option C, gas, option D, none of the above. Now, first of all, what is thermal expansion? Thermal expansion has to do with the expansion due to heat. Application of heat cause expansion. Expansion is actually where the particles start to move away from each other. Now, if I have the three states of matter, this is solid. For solid, the particles are closely packed. Now, this is liquid. The particles relatively not closely packed compared to gas. It has little intermolecular space. Now, if this is gas, gas has a high intermolecular space. The space between the particles of a gas is quite large compared to the rest. So if this is solid, this is liquid, and this is gas. Now, let's assume that we apply equal amounts of heat. Apply equal amount of heat, let's say 50 or 10 joules of heat. Apply here 10 joules of heat. Apply here 10 joules of heat. Now, which one do you think will will the particles move further from each other? Just think, if you apply heat to this, it will take a little time before these particles will move further away. It will take a little time before this particle will move further away, but the time here will be smaller compared to this because these particles are closely packed. We're going to take a lot of time. The time here for this guy to expand will be large compared to this. However, little time, apply 10 joules because there's a large intermolecular space between them already. They move far apart. So in which of these are we going to have the highest thermal expansion? That means expansion due to heat, separation of these particles due to heat. The answer is not solid. The answer is not liquid. The answer is gas. So this is quite easy. The highest thermal expansion is found in the gas state of matter. So I hope I can clean this. If you are writing this, so just pause, then you continue, you play back again to continue. We'll move to the next question, which is question number 12. Question number 12. Question number 12 is dash is least compressible. Dash is least compressible. A, solid. B, gas. C, liquid. D, plasma. Dash is least compressible. Now, compressibility actually means we are trying to compress, trying to decrease the intermolecular space, trying to decrease the space between the particles of different states of matter. Like we've drawn before, we drew this something, in the previous question, we drew something like this. For solid, these guys are what? Closely packed, that there's no intermolecular space between the particles. For liquid, there's little intermolecular space. For gas, we have large intermolecular space. So if this is solid, this is liquid rather, this is gas. Now, if you arrange yourself in your school on a seat that there's no space between all of you, all the students in a seat, in a long bench, arrange students in the long bench, and there's no space between them, and someone is asking you to shift. Now, I cannot compress all of you because there's no space between the students again. So that's what we're trying to say. Which of these will have the least, which is least compressible? I cannot compress solid again, right? Because there's no space for me to compress them. Compressibility means I'm trying to reduce the space between the particles. Now, there's space here, so we can easily what? Compress it. So liquid is slightly compressible. Solid is incompressible. Now, gas has a very large space, so it is easily compressible. Compressible means that we are trying to reduce the intermolecular space, the space between the particles. So which one will be easy for us to compress? The answer is gas, followed by solid. Followed by liquid rather. Solid is least compressible. So you should know that solid is incompressible. Why? Because there's no intermolecular space. There's no space between the particles. Now, liquid is slightly compressible. Why? Because we have little space between the particles. Gas is very compressible. Why? Because we have large intermolecular space. That is why a gas can occupy a small volume. Now you see this big volume, I can put 50 grams of a gas. 50 grams of a gas. Now inside this small volume, I can still put 50 grams of that same gas. Why? I will compress it into this place. I'll try to reduce the space between the particles of the gas. So which is least compressible? The answer is not gas, rather. The answer is not liquid. The answer is not plasma. The answer is solid. Solid is least compressible. So first, if you're writing this, be fast, or pause the video, then play back when you're done writing. So we move to the next question, which is question number 13, I guess. Yes, question number 13. The boiling point of pure water at 710 millimeter of mercury is A, 100 degrees Celsius, B, less than 100 degrees Celsius, C, greater than 100 degrees Celsius, D, none of the above. Now, pause the video, right? If I were you, try to answer this question. Like I'll always say, please try to read this topic before coming to answer my question. However, please, I'll also urge you again to share this video. Tell people about this page. Tell people about us. Tell people about Evernoic. Subscribe, and then turn on the notification button rather, so that once I drop a video, you'll be notified. First of all, what is boiling point? Boiling point, some of you will just define boiling point casually. You say boiling point is the temperature at which a liquid boils, or at which a liquid turns to vapor. Now, that is not actually correct. It's not totally correct. Now, boiling point is the temperature at which a liquid boils at atmospheric pressure. Atmospheric pressure affects boiling point. I don't know if you grab. I'll repeat again. Now, boiling point is the temperature at which liquid boils at atmospheric pressure. If you don't add atmospheric pressure, then what you are defining is wrong. Because the boiling point of water varies. It's not constant. The boiling point of pure water, even if it's pure, varies. It depends on the external pressure. Now, the external pressure determines the boiling point. At 1 atm, the boiling point of water is 100 degrees Celsius. Now, if the external pressure is lower than 1 atm, the boiling point of pure water will reduce. So the higher the external pressure, the higher the boiling point of pure water. So like I said, now water will boil at 100 degrees Celsius when external pressure is 1 atm. So what are we going to do now? We are going to relate boiling point and the pressure given to us. But one thing you should know is that 1 atm is equal to 760 millimeter of mercury. So water will boil at 100 degrees Celsius if atmospheric pressure is 1 atm. And we all know that 1 atm is what? 760 millimeter of mercury. Now, but if you check, the pressure given to us is not equal to 760. It is less than 760. If it is greater than 760, water will boil above 100 degrees Celsius. However, it is less than 760. 710 millimeter of mercury is less than 760 millimeter of mercury, right? So can I say that 710 millimeter of mercury is actually less than 1 atm? So since it is less than 1 atm, water will boil at a temperature less than 100 degrees Celsius. Water will boil at a temperature greater than 100 degrees Celsius if the atmospheric pressure is greater than 1 atm. Water will boil at a temperature lesser than 100 degrees Celsius if the atmospheric pressure is less than 1 atm, which is less than 760 millimeter of mercury. I said water will boil at 100 degrees Celsius when atmospheric pressure is what? 1 atm. 1 atm is equal to 760 millimeter of mercury. The pressure given to us is 710 millimeter of mercury. 710 millimeter of mercury is not equal to 710 millimeter of mercury is not equal to 760 millimeter of mercury. So water will boil at a temperature below 100 degrees Celsius. So the answer is not 100 degrees Celsius. The answer is not greater than 100 degrees Celsius. The answer is less than 100 degrees Celsius. So that's it. A simple question. All right. So if you're writing this down, pause the video, write, then play back because I want to clean to save time. We move to the next question, question number 14. Question number 14. The temperature and pressure at which the three phases, solid, liquid, gas, of a substance coexist in equilibrium is called option A, critical point. Option B, triple point. Option C, transition point. Option D, off point. So, question number 14. If you are writing me fast, pause the video, then write so and try to answer the question yourself, because I believe you've read this topic, so you should be able to answer this thing yourself. it does not really mean that you must get the answer. So you play back to see the correction and see, or the solution to see if you are correct rather. So the temperature and pressure at which the three phases or the three states of matter of a substance coexist is called dash. Now, first of all, we're going to look at the temperature pressure graph for the three states of matter. We're going to plot a graph before I answer this question. We're going to plot a graph of temperature against pressure. Now, this is how the graph looks like. So this part is called solid. This part is the solid phase. This is the call for the solid phase of a substance. This part here is the liquid phase of the substance. Then this down part here is the gas phase of the substance. Now, if you check very well, I'm going to show you 2 points. Critical point and another point that is the answer. Critical point is not the answer. I'm going to show you 2 points. There's this point here where the liquid and gas phase coexist, where there is no boundary between the liquid and gas phase. It is this point. At this point, if you check, the graph did not extend this way, so that there will be a boundary that all this side, this part will be for gas and this part will be for liquid. No, it stopped here. Now, that point where gas and the liquid state of the substance coexist, where there's no boundary between this gas state and the liquid state, is what we call critical point. This is the critical point of the substance. If we trace this down, I'm going to call this, because it's towards the pressure axis, critical pressure. This critical point, the point where the liquid and the gas state of the substance coexist, where there's no boundary between the liquid and the gas state. Now, this point here, this axis is called critical pressure. Now, if I trace it to the temperature axis, I'm going to call it critical temperature. So take note of that. That's the point, critical point. Critical point is a point where the liquid and the gas coexist, where there is no boundary between the liquid and what? And the gas. Now, there's also another point where the three substances coexist. Now, if you trace gas to this point downward for gas, this same point to this side is liquid, this same point to this side is solid. I'm going to trace it. I'm going to point it rather, this point here. Oh yeah, gas to this side, everything from here to this side, gas. Oh yeah, everything from here to this side is what? Liquid. Everything here to this point is also what? Is what? Solid. This is triple point. Triple point. Triple point is the point at which the solid, the liquid, and the gas phase of a substance coexist. If I trace it down, this is triple point pressure. If I trace it to the temperature axis, this is triple point temperature. So water can exist in its triple point. That means where water, the solid, gas, and liquid state of water coexist. So the answer is not critical point. The answer is not transition point. The answer is not off point. The answer is triple point. Triple point is the temperature and pressure at which the three phases of a substance coexist in equilibrium. So if you are writing this, be fast. If you are writing this, bit fast so I can clean the board. So you pause, then you write. So I can forge ahead. We move to the next question. Question number 15. Question number 15. White zinc oxide turns to yellow zinc oxide is option A, physical change. Option B, chemical change. Option C, oxide change. Option D, all of the above. So, like I said, these are simple questions. You've read this topic, you should be able to be answering all these things. You first of all read them, pause this video, answer them, play back to see my solution and see if you're correct. Okay. Change. A temporary change. Substance. Physical change, and we have the chemical change. So, class, for physical change, it is easily reversible. No new substance is formed. No new substance is formed. Chemical change, not easily reversible. New substance is formed. Now, the question given to us here is a change between zinc oxide to zinc oxide. Is there a change? Yes, just color change. One is white, then the other is yellow. Is there a change? Yes, change in color. Is there a new substance formed? No, there is no new substance formed. The change is zinc oxide to zinc oxide. No change. No new substance formed. However, there is a change. So it is called physical change when there is no new substance formed. So the answer is not chemical, it's not oxide change. The answer is physical change. Physical change. That's it.